to welcome Peter Winter, who will today give us the final result of the G-2 experiment. Peter has been at CERN in 2004 as a summer student and luckily came back today to give this seminar. He did his PhD in 2005. He finished it in 2005 in Bonn and Jülich, and was then a postdoc at University of Illinois at Urbana-Champaign and at the University of Washington, working on various Muon precision experiments in collaboration with PSI. Since 2012, he's a staff scientist at Argonne National Lab, working on G-2, as you may guess, but also Mu2e and on the Dune experiment. And since 2 years, he's also the spokesperson of Muon G-2, and we look forward to your seminar. The floor is yours.
Thank you very much. It's a pleasure to be back. More than 20 years ago, I was here. First, I came here to CERN for the ATRAP experiment with my professor from Jülich, and then he also made it possible for me to come as a summer student. It was a really great time. I am happy to be back, and it's a great laboratory. So today, I want to give you a final moment of the muon. It's not the final moment of the muon, of course. We have plenty more muons to come, but it's the final moment for this experiment for the G-2 analysis that we perform. So I'll give a short history and motivation. Then I'll say a few words on the comparison to theory prior to this final result, and then go through the details of our experiment. So just to introduce the muon, of course, is a very powerful tool in the laboratory, not only in Muon G-2, but worldwide used. It's sensitive to new physics because of its larger mass compared to the electron. And it also is light enough in our case that the decay has no hadronic decay modes, which just makes for a clean decay mode in the detection. It, of course, decays into a positron, into neutrinos in our case, because we're using positive muons. And it has long lifetime so that we can actually accelerate and store it nicely, like you also do here in your own environment. And for us, it's very important that it has a self-analyzing decay, as you will see later on. Just a little bit history. Of course, it started all out. If you think of a classical current loop, you would have expected that G was 1, but early on, very quickly, G was detected to be 2, and then Dirac's famous theory, of course, also predicted G for the electron to be equals 2. But experiments quickly saw for the electron that it deviated, and Schwinger's famous Schwinger term would explain this initial discrepancy seen by those experiments. And so the experiments continued. Also, the muon showed deviations from G being 2, which we then phrase in terms of this anomalous magnetic moment, or the magnetic anomaly A mu, which is the relative G-2 over 2. What is this about? Why do we do the measurement? The basic principle is we know the terms that contribute, the QED, of course, and I color-coded here a little bit in this value. The contribution size, QED, the largest one, but the best known. The QCD, that's the one where, of course, theory puts all the effort on, because it's not only a large contribution, but its error is the dominant one for the standard model calculation. And then there are other contributions, electroweak. And of course, if there's anything other that might contribute to a mu, we might see it by comparing the theoretical and the experimental values. So it's really the QCD that drives the uncertainty in the theory side, and especially the hadronic vacuum polarization. We just got a new value from the theory initiative a week before our final result, and I'll comment on that one on the next slide. So let's first look at the big picture of the theory, because there are two approaches. One is a long-standing approach using dispersive integrals, where they have input data from E plus, E minus experiments all over the world. And that is, you can think of it as in the diagram below here, where this muon diagram of the hadronic vacuum polarization, if you cut that open and flip it over, it relates directly to the E plus, E minus cross-section going into hadrons. And then the mu hadronic contribution at lowest order to the hadronic vacuum polarization is given by this dispersive integral. Due to this 1/s factor, the largest contribution comes from the 2-pion channel, which is about 75% of the whole contribution. So that's where the experiments really have to work hard to give precise input data that then gets into this dispersive calculation. The other hand is the ab initio calculation using lattice QCD, which has made tremendous progress over the last year simply because the computing power and, of course, the techniques have improved, and they have now reached a similar size precision to the hadronic vacuum polarization based on the dispersive approach. And just to give this a little bit put this in a different size, this blue bars denote the contributions. Note that the x-axis is logarithmic, and the hatched areas are the uncertainties. So for QED, you don't even see any uncertainty on this plot because it's so tiny. And you see also at the top the incremental progress that the experiments made, many of them, of course, here at CERN. And you see that they started to probe more and more contributions until recently the BNL even probed the electroweak part. And if there's anything new in this question mark box below, then we should also see its contribution in the experiment. So the basic technique is we're putting muons in a storage ring. They have a cyclotron frequency, and their spin precesses given by this combination of Larmor and Thomas precession. And we are really looking at the beat frequency omega A between those two. If G had been exactly equals 2, you would see that spin and momentum are locked in phase with each other. But since it's not, there's this beat frequency that we will see in the experimental setup later on. There are many experiments that have been in the books. CERN-2 got to 270 part per million precision on the mu value. You see here the nice wiggle plot. That's this precession frequency that we are looking for to detect in all these iterations of the experiments. But then this was not storing the muons, so can we do better? Yes, we can. You can add an electric field for vertical focusing so that the muons go around many times in your ring, but that generates a motional magnetic field which would contribute to the omega A spin precession. There are two techniques. Either you run at this magic momentum, which was pioneered here, and then to first order this electric field term cancels, or there's another iteration being built at J-Park in Japan, where they simply don't use electric fields. They use weak magnetic focusing to keep the muons vertically stored. And so to first order, this is simplified, but it brings over the point. To first order, we really measure two variables, the omega A and the magnetic field, and that gives us access to the A mu. And then there were more iterations. CERN-3 pioneered this magic momentum. BNL even improved it further with many more improvements to these experiments, and Brookhaven pretty much left us with this about 3.5 standard deviation tantalizing discrepancy of the experiment versus the theory at that time. And that has motivated redoing the experiment at Fermilab because, and this is the two new experiments that were motivated. On the right-hand side is our experiment that I'll describe. On the left is this different version with a much smaller magnet because they're not running at the magic momentum. And you can see that they have different setups, but I'm now focusing on the Fermilab iteration since that has just finished. The basic idea for going to Fermilab is that we were, within reasonable time, we could get 21 times more muons, which gives us a factor of 4 or more in statistical precision. We could get, so that we could get to 100 part per billion on the statistical uncertainty. We could get improvements through new hardware or upgraded hardware to get the systematics down to about 70 part per billion for both observables independently. And bringing that all together gives you 140 part per billion final precision goal, which was 4 times better than Brookhaven. And just to put this in perspective, Fermilab has these nice big bisons, and somebody did the estimate that 100 part per billion, 140 part per billion is roughly that if you have the bison on your scale, you could see if we added a sunflower seed or not. So it's a pretty impressive relative comparison. Okay, so what's the situation? The theory, of course, has evolved over time, and you might have noticed that the discrepancy has shifted. So I'll go a little bit over the history since our first result. This is just before our first result came out in 2020. The theory initiative, about 100 more theorists around the world, are working together to make a recommendation for the standard model value with their best knowledge at that time. And at that time, there was in green, always on those plots, is the dispersive approach. And you can see the different input experiments, 5 of them that were used to generate this TI white paper, Theory Initiative White Paper 2020 prediction at that time. There was also lattice QCD, which always will be an orange on those plots, but the uncertainty was so large that the Theory Initiative at that time said we are not including lattice because we are waiting for improvements to see where it will settle. So then we had finished our run 1 data. On these plots, over time you will see how the statistics accumulate. This is just 5% of our total data set, but it was our first run, but we analyzed it and put out the first result. And you can see on the plot here that the first result very much were in agreement with the Brookhaven experiment, and it brought the discrepancy with the standard model to about 4 sigma at that time. But right on the same day of our result, there was a more precise first full calculation of lattice QCD for this hadronic vacuum polarization, which was very much closer to the experimental result. Since then, the situation on this dispersive approach has even been also more confused because the CMD3 result came out, which is now very close to the experimental result, but in tension with all the other input data from the other experiments. That's why there's, at the moment, no conclusive statement from the Theory Initiative on that approach. We, in the meantime, had, in 2023, analyzed 2 more years of data and gotten about 4.6 times better in terms of statistics. So we really started to settle the new world average by our own experiment. Brookhaven played less and less of a role. And you can see the second result was spot on again. Now, just a week before our final result was coming out, the Theory Initiative has now gone through a lot of work, and they have now recommended a new value based on lattice QCD only, which is shown in this orange point, and you see that one, of course, has actually all the other calculations that have come out have been in agreement with this first precision lattice QCD, and the tension has gone away. But on the other hand, you can look at it that way, that the tension has now shifted from between experiment and theory to within theory, because there's still a big question, why do dispersive approach and lattice QCD, which in principle should agree with each other, do not agree, and why is there this one experiment that has a difference to the other one? So there will be still a lot of work going on, and I'm sure that we learn a lot simply out of answering these ongoing puzzles. So that's the story of the theory to experiment comparison. Now I really want to shift focus onto the experiment. In the meantime, we have finished our data taking. We have taken 6 years of data. We've reached our 21 more times muons, and that was a real big success thanks to this great support at Fermilab of the accelerator and many other resources. This is a small history of the experiments as we are coming to a conclusion of our main measurement. You can see we started out in 2008 with the proposal submission. We had this big move in 2013 where the superconducting coil came from Brookhaven to Fermilab. Actually, since I saw the SC outreach video this morning, it reminded me you had your own move at that time when the coils came in that video. This one was a little bit bigger, I guess, but nevertheless, we all have our big moves The first muon came in 2017, then 6 years followed 6 years of physics data taking, and now we are here at the conclusion of this effort. The experiment takes place on the Fermilab site in the so-called Muon campus. We get polarized muons at the magic momentum that are being brought into the experiment in this Muon Campus 1 experimental hall. They are produced from protons that impinge on the former anti-proton target, hence the name AP0, and produce pions, which then have a long decay line for us to produce muons so that we get the muons into the storage ring. Once we have those muons, we have to bring them into this beautiful magnet. The magnet is the blue in this picture is here not yet covered with insulation, is the return yoke. You can see we have the return yoke that spans the outside, and then the muon region where we have a lot of tools to fine shim the magnetic field, because homogeneity is very crucial for us, since we need to know this magnetic field to 70 parts per billion, which is challenging for a 45-meter long magnetic storage ring. To bring the muons in, since there's the outer yoke, there's a channel with a hole that has a very small aperture inflector magnet, which creates an opposite magnetic field so that the channel has a field-free region, and the muons have to be threaded through this very small aperture that has this magnetic free region. So that's a bottleneck for us where we lose a lot of muons, but still that was enough for us to get the required statistics. Now, since the muons come in slightly offset from the ideal orbit, after 90 degrees on this dark blue line, if you follow, they traverse the ideal orbit, but with a wrong angle. So we have a very fast kicker magnet that gives them a strong kick to offset them by the right angle, so that after the first round, they really end up on the light blue ideal storage orbit and get stored. Otherwise, they would be lost after one turn or half a turn already on the inside. The other confinement we need is the vertical confinement, as I said earlier. So we employ these electrostatic quadrupoles. They are pulsed with the injection, similar to the kicker. And those are these 4 plates covering about 40% of the storage ring, indicated by those yellow areas that we have the muons confined. So one thing that is new in the run 4, 5, and 6 data that I'm presenting today is that we added this RF system, and I'll come back to it later on to give you an idea what it helped us improve. Then the main detectors for the omega A are 24 calorimeter stations, lead fluoride crystals. They this one was completely built from new, and had much more improvements, especially the segmentation compared to Brookhaven allows you to reduce the pileup systematics. And we had a beautiful laser system installed that monitored and gave us access to control the gain and assess many of the gain-related systematics, because a gain shift means an energy threshold shift, and energy threshold is, as you will see, crucial for us to make this experiment happen. The other component that we need to measure is the magnetic field. For that, it's a sequence of various steps that bring together full information of the entire magnetic field where the muons are stored. First of all, we have about 400 fixed probes above and below the vacuum chambers that constantly monitor the magnetic field at all times. Every 3 to 5 days, we are sending out this little trolley which lives inside the vacuum chamber, but of course, if it's inside where the muons are stored, it doesn't work in parallel. So it can only run every 3 to 5 days to give precise maps of the full storage field. And then we have a very specially designed absolute magnetic probe that gives us the reference to an absolute magnetic scale. We have other detectors, in 2 locations inside the vacuum chambers. In front of the calorimeters were those straw trackers that give us information on the decay positrons and their trajectories. And that gives us information back on the muon beam distribution, for example, here overlaid. So that is relevant because we need that to understand what the magnetic field the muons actually see is. And it gives us a lot of information on many of the beam dynamics related systematic uncertainties. And this is just a video of the components if you were inside a muon, as a muon. We mounted a little camera for a special run on the trolley, and we are speeding up the speed of the trolley virtually. It usually takes about an hour for the trolley to go around and back. So this is way faster. Here's where the muons would come in from the left. At the first round, they would be offset from the ideal orbit. This is one of these electrostatic quadrupole focusing areas. Then at 90 degrees, we have these two kicker plates that then steer the muons on the right orbit. This needs to be very fast because the muons go around with 140 nanoseconds. So by the second turn, the kicker magnetic field should already be turned off so they don't get overkicked. Here on the right is where normally the trolley is parked inside the vacuum while muons are stored and then can be brought in automatically to make its round. There's the calibration probe that also sits in the vacuum because every now and then we calibrate each of those trolley probes against an absolute standard. Another ESQ section. I didn't mention, but we also have collimators that are normally inserted to shape the beam during the early time after injection. For the trolley, of course, we need to put them up just that it can pass. But normally they are inserted so the muon beam gets scraped and has a nice circular aperture. And this is one of these beautiful straw trackers in front of the calorimeter. And I think that's pretty much it. Okay, so this was the big picture of the experimental technique and the components. Now let's look a little bit more into what we actually measure. I told you early on this is to first order what we measure. But we can rewrite that with simple formulas into a ratio of two frequencies, omega A and omega P tilde. The denominator is nothing but a reference system, so to say, for the magnetic field. Because protons, we know they are a Larmor frequency. The G factor, we know that, so the protons in this water sample act as a reference to give us a calibration for the omega A frequency in that same magnetic field. The other components, those two black ratios, are very well known from other experiments at the 4 and 22 part per billion scale. Remember, we are aiming for 140 parts per billion, so they are negligible for our purposes. Of course, we take them into account, but they are small enough that they don't affect our error budget much. Okay, so what do we really measure? We don't measure omega A and omega P prime on the left side directly, but it's more complicated than that, and I want to go through the steps of what all we have to assess to really get to that ratio on the left side before we can publish a result. First of all, the famous wiggle plot, that's the omega A measured frequency. It's we indicated with measured because it needs beam-related corrections that you will see in this black term in the denominator. The basic principle is the muon decays, the ensemble of muons decay over time. They are polarized, so their spin roughly precesses at the same speed. And the electrons, the decay positrons, sorry, in our case, then curl inside towards the calorimeters where we detect their energy and time. Due to the parity violation in this decay, the highest energy positrons, if we only select those, they are preferentially following the spin direction. So if we look at those, over time, their number distribution above the threshold, as indicated by this blue changing area, changes over time. So if you just do counting of those positrons, then you get that famous wiggle plot. And it's characterized by the muon lifetime, which is the linear decay, and the wiggle, which is this omega A frequency. So to first order, a 5-parameter fit, as shown here, describes the most part of the spectrum. But the reality, of course, sorry, that was one. The reality is a little bit more complicated because the beam, the muons stored, they also undergo other frequencies like betatron oscillation in both the vertical and the horizontal direction. And so if we fit this beautiful wiggle plot with this red curve indicated by the simple fit, and you look at the fit residuals, the frequency Fourier transform, then you get other peaks. The most dominant is the coherent betatron oscillation. And since some of them are close to the omega A frequency, we have to take them into account. So the actual fit in the data is way more complicated than this. It has way more parameters that reflect these beam dynamics of the muon beam. And if you squint, actually, after we apply the full fit, that's way more complicated than the simple one I've shown here, you can see that the red spectrum, which assesses the residuals after we accomplish the full fit, is very flat and has addressed these main beam dynamic related effects. For the field, we need two components. We need an actual field measurement of where the muons are, which is mainly driven by taking 9,000 slices of these 17 probes around the ring every 3 to 5 days. These 9,000 slices, a few of them indicated on the left, then gets translated into multipoles over the entire azimuth. The blue one is the relative field change, and then we can decompose that in multipoles like the dipole, the normal quadrupole, or skew quadrupole, to get a description of the field in this analytical description of multipoles. However, the trolley only gets sent out every 3 to 5 days, which is indicated by those red stars. So in between, we have those 400 fixed probes that are in 72 locations in groups of 4 or 6 to monitor the slow field drift. Now, they give less information because they do not have this fine map that the trolley provides, but they give enough information to correlate a trolley field map at earlier times to one later, and then there's a complicated analysis that connects the two and makes corrections for any deviations of the less knowledge the fixed probes have. And then in the final end, we also need to relate that to these protons in a spherical sample. We do that by having a very well-designed cylindrical water probe that measures from time to time compared to the trolley probes, pretty much at the beginning and end of each data taking. We did a full trolley calibration. This probe was characterized for its effects of its own materials on its field measurement in a solenoid at argon with about 15 part per billion precision. We also did a lot of consistency checks because that's an important and tricky calibration. We had, first of all, a spherical water probe outside in the solenoid that got cross-referenced to this cylindrical probe. We also compared to the future JParc probe that they want to use with ours so that the two experiments will have a consistent calibration with respect to the magnetic field. And colleagues in the G-2 experiment developed a new helium probe that has different systematics and therefore really made our understanding of the calibration very solid. And then you have this beautiful muon distribution from the trackers that gets inferred from the decay positrons. And so for each data period where we measure the magnetic field, we fold the magnetic field shown by those white contour lines with the muon distribution to really give the value of the field that the ensemble muon set experienced. Because if the muons don't live on the outer edges, then that magnetic field has less relevance, and that's important for us as we need to know the absolute integrated magnetic field. On the nominator side, we need corrections for the beam dynamics. So let me give you an idea of the individual contributions. I already told you earlier that the formula is actually more complicated. So in case you have an electric field like we do, we need to correct for the fact that not all muons are on this ideal magic momentum. On the right, you see this momentum distribution, and that relates to the equilibrium radius. So the squared of the equilibrium radius is the driving parameter that we need to calculate this correction. And it's the largest one at 350 part per billion. So you want to make sure you get that one right because it's way larger than the actual precision we are aiming for our mu measurement. Another one that's also pretty large is the pitch correction. In this term above that I have simplified the formula, there would be an additional beta.b term for the fact that the muons are not all in the horizontal plane, but going up and down. And that one is driven to calculate by the vertical y-squared distribution, which we also have access through the tracker, straw tracker information. So that's data-driven that we can determine both of these. And then a phase change. The muons, the ensemble comes back with a certain phase with respect to their momentum at the injection, and any change of that relative phase outside of the omega A precession, a phase change of that muons ensemble over time, phase change is a frequency. So if anything changes that average phase of the muon ensemble, we also need to correct that, and we have actually 3 mechanisms. If the beam moves, for example, inside, and due to coupling of the phase to the acceptance, you get a change of the accepted phases that we see, and that's a change in the frequency. Differential decay, high energy positrons and high energy muons and low energy muons that we have different lifetimes and different phases. So as they decay differently, that also changes the phase over the ensemble. And if any muons get lost and they have different phases compared to the whole muon distribution, those also offer phase changes of the muon ensemble. So these are the 5 contributions, all data-driven mostly, with some simulation input, but mostly accessed through our own data to determine them. Nuclear magnetic resonance probes that we use for the main measurement of the field are very precise, but don't have a large bandwidth. So fast magnetic field transients, especially because we have these injected pulse systems at 10 milliseconds every 10 milliseconds, can create eddy currents that then generate magnetic fields. We generate magnetic fields in the kicker magnet because it's pulsed very fast. We have magnetometers using the Faraday effect to assess those in dedicated runs. And we actually were surprised to also see an effect in the quadrupole plates, but the vibrations of those plates, because of the mechanical resonance being unfortunately close to this frequency we pulse them at, led to also magnetic fields. We discovered those and designed a special peak trolley because the normal trolley cannot run inside the quadrupoles when they are pulsed. So we designed a special peak trolley with a peak probe that could run inside the quadrupoles. We could pulse them and then still access and measure this effect. That was actually the dominant systematic, to our surprise, in the run 1. But luckily at that time, we were still statistics dominated. So over time, we reduced it dramatically to now 20 parts per billion from 90 parts at that time. Okay, so I want to now give you the result, go over the uncertainties for the result, and then give you an impression of some of the improvements. I know time is limited, so I picked 3 improvements for this new data set. There were many more, and I can't do justice to all of them, but I wanted to give you a flavor out of 3 different ones that are representing the whole spectrum of improvements that we saw. But before we come to the result and that part, I really want to say it was an incredible team, incredible collaboration of about 200 people. This is at the unblinding meeting on May 20th, so about a month ago. Most of the people were on Zoom, but it was an exciting moment where you open the envelope and you get your frequency of the clock system that we had detuned to apply the correction factor to get really the correct result. And if you saw the result before the unblinding on this results plot that I showed you, it would be probably over by the cafeteria somewhere, because we had really a large blinding to really suppress any biases. And the collaboration is maybe not the most typical particle physics collaboration, because we are comprised of particle, nuclear, atomic, optical accelerator, and theorists. because you saw there's a lot of beam dynamics, a lot of atomic physics in these nuclear magnetic resonances that all had to come together to make this experiment happen. Okay, so I am now taking out the theory complexion and leave the focus on our result. We are really unblinded and came spot on again out. That was a real big relief after adding about 2 more times statistics. And with that, the overall final result of our data set for all 6 years had an improvement of more than 4 times compared to Brookhaven, and will certainly be the reference for many years to come, as it's not easy to improve on this experiment quickly. This plots the same on the right, except it's broken down into a finer subset of data sets that we actually individually fit and analyze, because there are different beam settings. And you can see that the overall consistency and the p-value plotted on the bottom right for this large data set comparison is very good and shows that the experiment actually is very good in agreement and shows a consistent result over many years of work. The systematics is plotted again in terms of this formula at the top, so the terms all match. First of all, this is for the run 4, 5, 6 data, the new 3 years of data taking that we added. We reached almost by itself the final 100 part per billion statistical goal with this data set alone. One key point you can take from this pie chart without looking into the details is that it's rather similarly distributed. The pieces are rather like a nice pizza dinner where everybody gets the same pie. So improving on this experiment in the future wouldn't be like just one single dominant systematic where you have a lot of improvement still left. You would really have to think hard to improve on all of them to make strides forward if we were ever to improve this experiment. In the middle, I didn't highlight, of course, these external constants are taken into account, but altogether, this data set alone gave us already 139 parts per billion. The goal was 140 parts per billion for the total data set. So as I said, I want to use a few moments here to give you an impression why run 4, 5, 6 again had, of course, better statistics, but also some improvements on some of the systematics. First of all, on the running conditions, I picked one out of the omega A section. I showed you earlier this Fourier transform if you do a naive fit of only 5 parameters, the striking dominant CBO oscillation. Because the beam has this coherent betatron oscillation going around the ring, and we have 24 stations, we actually see this betatron oscillation as a beat frequency of omega A versus this betatron oscillation, and it shows up at the CBO frequency peak. And it's relatively close to the omega A, so we need to make sure that none of it leaks into the omega A. What we added in run 4 was an RF system that, on top of the high voltage applied to the electric quadrupoles plates, we had very early on for about 6 microseconds a RF signal, which acts like a forced harmonic oscillator. So if you are on your swing in the playground, you normally do the right motion with your legs, but we kind of had it out of phase so that the overall mean of this distribution of the coherent betatron oscillation was dampened, the average of the muons ensemble. And that it works is shown in these 2 plots. On the left is the RF off, on the right is the RF on, and then the bottom is the projection of those 2 beam running conditions for the mean of this oscillation amplitude. Now you might say, I don't see a difference. I honestly don't see a difference, but it's really the mean, and what your eye catches is the width modulation, which, so I really made sure the person who created these plots ensured me that they are different. But you can also see the numbers. If we didn't take into account the CBO at all, the left picture would give us an 800 part per billion correct effect that we didn't account for. The right one, 80 part per billion. So by just reducing this through the RF, we already tremendously reduced the effect. But of course, we are fit for the CBO to reduce it even lower. So these 880 was just if we did nothing about it for the CBO in our analysis. For that reason, we applied this RF in steps, first to the X plates and then to the Y and X plates to dampen both motions. And we split the data sets according to those operating conditions just to see that they are consistent and we understand that the RF didn't introduce anything else that we hadn't anticipated. We also added new detectors in this final data set. This was an addition of a so-called minimally intrusive scintillating fiber detector. It might not show up on the pictures, but you might see the reflection of those fibers. In this case, they are vertical. We also had a detector option where it has horizontal fibers, so you can really assess the beam profile of the muons directly. Now, this is an intrusive detector, so it only could run in dedicated studies, but it would give us more information on the actual beam distribution. And for that, I want to come back to the electric field correction. Remember, it was the largest correction that we had. And now we had 3 detectors that gave us information to determining this 350 part per billion correction. The trackers and the CALOs both have access to giving us the correction through different techniques. But the mini sci-fi gave additional confidence because it was a direct measurement of the muon beam distribution, whereas the CALO and the trackers only see the decay positrons. And it therefore helped to understand also the uncertainties related to the tracker stations. So all of them give us access to this momentum distribution. Here plotted again, like before, for those 4 different running conditions of the RF that we had. And this is a plot of the distribution of this correction versus individual data sets, as we have not only those run 4, 5, 6 data sets, but also finer data sets where we do different fitting to just understand really that we understand the whole data set in all its granularity. And you can see the green points were new in this analysis and gave us additional confidence that our uncertainty band indicated by the gray was very well determined. Finally, an analysis improvement to give you a flavor also out of the magnetic field sector. We needed to measure these magnetic field transients from the kicker plates. And for that, we now, in run 456, had actually 2 iterations, 2 hardware systems, a fiber magnetometer and a free laser magnetometer. Both use the Faraday effect to see the rotation of light, polarized light in a crystal, depending on the magnetic field. And those 2 analyses of both magnetometers came out very consistently here in red and blue, the measurement versus time over this time where the muons are stored between the dashed lines. And so that really needs to be accounted for. You can see that there's an exponential decay of that small transient that is relevant for our precision level. We also had in the analysis improved spatial modeling because these magnetometers are intrusive, so we can only take them at the cost of not running with muons. Therefore, we wanted to optimize, of course, our time and only took these measurements in certain spots, but we have to extend that over the entire kicker region, which is quite large. And so the modeling of that had also been improved. Finally, in my last few minutes, then give you the summary flavor of the whole data set. Statistical uncertainty combining all 3 just got us a pinch below our original precision goal, which is great. Even more, the systematics, we beat the TDR goal of 100 parts per billion overall to 78 parts per billion. And that's why also our overall goal of 140 was surpassed by 125. Actually, I should say this should be 127 for the AMU because of those external constants. So nevertheless, our final precision goal of 127 parts per billion that we reached surpassed the TDR by quite a bit. Okay, where are we going from here? Now I put back on the theory as well. You can make your own judgment. I think G-2, no matter what, is a benchmark for any standard model extension in the future because you see the experimental value stands now on very solid footing. There's not much doubt about that. Many experiments over time have shown that, and we have settled on a quite precise result. And we will see where theory is going. Theorists will continue working on understanding, is it the orange, is it the green? What are the differences? Where will we settle? But I think that alone is also a tremendous accomplishment, because theory has made tremendous strides forward and has now come to the lattice QCD being at the similar level of the dispersive approach. And I'm personally looking forward to the resolution on the answers why the plot at the moment looks like this. We are not done on the experiment, although I said final moment. That's the final moment for the magnetic moment. We also have data coming out, hopefully soon, on a search for an electric dipole moment, which would be a tilt in the precession plane of the muons. So with these straw trackers, we actually also have access on the tilt angle of the precession plane. And in the initial result that we hope to get out soon, based on the first years of data taking, we will roughly be at the Brookhaven sensitivity. But overall, we can gain up to a factor of 2, moving the search for the muons EDM forward. We also are sensitive to BSM physics, like CPT or Lorentz violations, or even some scalar and pseudoscalar dark matter candidates. So that's also something we will hopefully get out the initial results this year and then, or next year, and then the full data sets in a time scale of 2 to 3 years. Of course, other experiments also are ongoing. I mentioned already the JPARC experiment is going to design a different setup where they don't use the magic momentum. So they will have a much smaller solenoid magnet. They will have a different technique. They have mostly tracking detectors for their omega-A precession. So they will have a good set of different systematics. And their initial goal will be something like the Brookhaven levels precision. And going beyond that will require that they produce many more muons, which is challenging in their technique as they produce them at low momentum, very cold muons, so to say, that they then get reaccelerated to have a low transverse momentum. The theory community and the data-driven input experiments will continue also their efforts to understand the current situation, especially in this green data plots on the plots. There are new data coming out from those experiments, especially on the 2-pi, 3-pi channel, which are the most dominant ones. And here I had the pleasure of visiting the Muon E actually this morning, which is taking their data to contribute from a different angle to this challenging problem, and hopefully will get fully approved to make this measurement over the years to give us an additional insight in resolving and understanding the theory for this experiment. And with that, I would like to really thank you and also extend my thanks to the many people that we often don't see behind these experiments, the accelerator control people that run the complex, the administrative staff, the technicians, engineers that all build these experiments. And typically on those photos, they don't get the credit because they are not there when we publish, but it's been a great success for Fermilab and this experiment, and we are looking forward to another set of Muon experiments that are being mounted. Thank you for your attention.
Thank you very much. The floor is open for questions. We start in the room. And in Zoom, you can use the raise hand feature. I would suspect that we have many questions. Who would like to start? Yes, Alex?
Yeah, so the theory error is now much larger than the experiment error, and what's I mean, how do we continue now? So now it's on the theorists to reduce their uncertainty, or?
So the theory, since right now it's solely based on the lattice QCD, has a bit larger uncertainty again because this is still work in progress, but they made it.
This was, yeah, so the uncertainty got larger from the Budapest Wuppertal then to the. So they included more people, or what? And then
it's more complex. I think one can say that one component is an average of 3 full calculations, but there are many more calculations that contribute as well in all the different parts. So it's an average over 3 at least, or many more input calculations on the lattice side. Therefore, that is larger. That's their current best recommendation, taking this complex sector of lattice QCD calculations alone into account. But we are expecting that this will improve over time as they are continuing not only resolving the screen data points and the puzzle there, but also the techniques and the supercomputing power that's available to improve further on the orange input calculations. So I think we should really stay tuned there, as it's going to be very interesting to just see how that resolves and what we learn from that. And yes, maybe the discrepancy between experiment and theory, while I think it's still open, might get resolved, as the orange point might indicate. But even then, as I said, the benchmark of this experiment stands undoubtedly against any future extensions for the standard model.
Question. Precise measurements of electron and positron depolarization frequency at lab have shown that they depend on gravitational modification of the length and shape of the tunnel, for example, due to moon tides, the level of the Geneva Lake, and other things. And this spawned a program that didn't go far of trying to look at gravitational effects actually with this frequency measurements. So I'm wondering if just by curiosity you looked at your results as a function of moon tides, time of the year, and things like that.
So we are actually looking at that in these additional analyses for the purpose of testing CPT and Lorentz variation, which is a test against sidereal variations. And the dark matter would look for variations in a more complex frequency space, in a larger frequency space, not only sidereal. So if we were to find a signal there, it's a good point that we should probably also understand if there could be any other external effects that could influence this.
And a small curiosity question. Can you measure muon lifetime with competitive precision from what you have? Because you're fitting this curve that depends clearly on muon lifetime. So.
We would not be sensitive at the level that has been done in the Muon experiment, which set the muon lifetime years ago very precisely. This would not give us a precision.
Up here, yeah.
I have a question on your magnetic field measurement, which is, you claim that it's very precise, and I'm sure it will be, because that is one of the critical inputs to your measurement. You are using a large number of NMRs to measure the magnetic field values, right?
Can you say that again?
The NMR, large number of NMRs values that you are using to find the magnetic field values.
Yes.
And that you do every few days, right? So these measurements that you are measuring will have certain points where you are measuring it, right, in the tunnel. Whereas your beam, it will be confined to certain momentum space. So how are you propagating the exact magnetic field that you require where your beam is at the size of the beam? Because your magnetic field will have some profile, some distribution. So are you taking some kind of interpolation that you are doing to get to the exact where your beam is, to get the exact value of magnetic field with certain uncertainties? And also when you are interpolating between the days, that plot that you showed, and that looks very conspicuous or rather interesting. So what kind of methodology you are adopting? Because it's very important that you get it right. So are you cross-checking that with some kind of simulation or modeling independently?
So on your second, let me answer the second part. We are not using simulation. It's very difficult to simulate the full magnetic field there. But certainly we see that the magnetic field drift we observe from those fixed probes over 3, 4, 5 days, compared to what the trolley would tell us the fixed probes should have seen, that there's differences. We call that, if you look in the publications, the so-called synchronization effect, and we take that into account. But it averages out. We get a 1/n reduction of that effect because it's rather random. And since we're taking so many field maps, we have the gain of accumulating more and more and getting a 1/n effect reduction of that. It is true the field probes have a certain size. They are maybe this big, a few centimeters in length and a centimeter wide. So they are sampling over a certain area. And we really want to, and we have 17 in the trolley. We are modeling these individual slices with 2D multipoles, so to extrapolate the field in between. But on top of that, we have done a really extensive testing of that. In the solenoid at Argon, where we have extreme homogeneity and can apply dedicated gradients, we can study exactly the effects of gradients on these probes so that we understand that the extrapolation is correct. We also understand the effect of the gradients on the probe measurement and that we get the right value of the probe out of that with these extensive tests. And then, yes, we have also studied that the 2D multipole description is actually valid because normally you would have a 3D Laplace equation that you would have to obey. So we also have understood that there's a negligible amount to make this 2D multipole extrapolation and then apply it to the full field. So there have been extensive understanding that really these extended probes, how we relate that to really measuring the field at all points in the entire ring.
So just to complete, what kind of uncertainties or what the order of the uncertainties that you are getting on these interpolations?
The total field is about 70 part per billion. The individual tracking and the calibration have about 35 part per billion out of that contributing. So this, what you referred to, is mainly inside this tracking line, which is just the 34, the first top 34. And that is driven especially mostly by the difference that the trolley sees after 3 days compared to what the fixed probes have predicted. Because the fixed probes have a much smaller granularity compared to the trolley field maps. So that is driving this uncertainty 34. But this also comprises effects like you referred to, extrapolating to the full storage area where we only have 17 sampling points and 9,000 slices.
Hello. So I have a question on trolley movement here. So when you move the trolley, are you breaking the vacuum inside the chamber? No? Because something is moving and, suddenly some friction or something can break the vacuum to a certain level.
So this is fully in vacuum. The trolley is automated. That's why it has this trolley garage where it can reside outside of the muons during the operation. So it's in vacuum, it's fully vacuum compatible, and it has fortunately not led to any problems with the vacuum. However, I didn't mention this due to time, because it's a can of aluminum mainly surrounding the probes. If you have a can of aluminum driving through a magnetic field and it bumps and rolls and pitches, it generates eddy currents. That came to a little bit of a surprise to us, but we can see those. So we did also dedicated studies where we drove the trolley a centimeter, took the measurement, drove a centimeter, took the measurement, and then compared it to driving it constantly as we do normally. And from that, we understood that these spikes actually almost cancel because they if you go one direction and the other direction, there's a canceling effect, and we have those also attributed. But it did not actually break the vacuum, but it had an effect on our magnetic field that we have taken into account.
Yes, please.
Thanks a lot. Why using straw detectors exactly? Why not other trackers?
I think that was a convenient option at that time. It was balanced between resources, and the technology was, I would say, relatively straightforward and a good choice for that environment. Yes, it's a little bit tricky because they are in vacuum and they can leak, but also they were carefully designed not to destroy our vacuum at any point. So it worked out very well, and the requirements on the detector were, I don't think, so large that you would need a fine-grained silicon detector, for example. So this was a good choice, and for the resources available for this project, had worked out very well and has superbly performed to the needs that this experiment had.
maybe I profit. If you go to the slide 55, you had your results split into the different samples, which included this additional RF correction, or not, if I remember correctly. Here, the bottom 4, right? Or apart from the average. Now, if I understood correctly, not when you apply this correction, no, when you apply this additional RF, you will reduce your correction by a factor 10. Yet here, the uncertainty is even larger. The uncertainty plotted here on the sample with RF than without. How does that come about?
So what I showed you was the effect if we didn't take that into account in the fit of omega A. The simple fit of 5 parameters is a simplification. We really take into account CBO in our fit. So this 800 versus 80 is really only if we didn't do anything in the fit. Therefore, the effect itself is much less than the numbers I quoted. And you see the omega A uncertainty was 30 parts per billion, and one component of that is the CBO. So it's much reduced than the numbers I showed. The fact that the error bars here are different for the no RF, even smaller, is mainly because that data set was larger, and we are statistics driven often in these data sets. Because that was the entire run 4, and then run 5 and run 6 had 3 subsets of the data. Therefore, you can imagine that there are differences in the statistical precision.
So that's the 5 and 6 there. Okay. Please.
Yeah, just one question. Maybe you have already answered it, but in your last slide where you're showing the different measurements of your experiment, but also from the others, so it's still unclear why the previous experiments were so far away, either from you or from the current theory.
So just to make sure, the green points here are not measurements of the Muon G-2. They are E plus E minus data. This one, I should have labeled the Y component. This is, so the bottom side is the theory calculation, and this is just input data from E plus E minus that gives one portion of the many items that the theory has to calculate in the hadronic contribution. So yes, this is not the same experiments like ours, and the current, to the best of my knowledge, there's no smoking gun to understand why 5 or 6 of them are on the left side, and the CMD3 result is now almost in agreement with the lattice QCD theory calculation. There's lots of work going on to understand this. New data on Babar and Chloe and other will come out that will shed further light on this, but there's no current explanation of this situation, why the green points have tension within them and why the bulk of the green points have tension with the lattice QCD.
Yes.
Is the final 140 that you have for your error, is that going to be the end of this story, or is it possible to do a factor 10 better on the experimental measurement, for example?
I think a factor of 10 better would be very, very difficult. You saw that for us alone, it took many years to get a factor of 4 improvement. Factor of 10, not only you would have to have much more statistics, but also getting these systematics, which are now rather evenly distributed, down by a factor of 3-ish then for each of them, would also require some thinking how to do that. And of course, in light of that the theory has yet to reach the same position and that there are questions that we want to answer, I also think that the motivation at this time to get a factor of 10 might not be there. We focus now on different areas. At Fermilab, we cannot run the Muon G-2 in parallel with the Mu2E experiment, which is being mounted. And I think we are better at the moment putting our effort into that search for possible new physics, which is going to happen in about 2 years. They're starting data taking. We could have run with mu- to improve on that, but that would probably not immediately have the same a strong case like the mu3 experiment, and as we cannot run in parallel, the efforts go to building a new charged lepton flavor violating experiment.
Up there on the left, please.
Hi, thanks for the talk. So what is happening to the ring now? Is just staying put for now? Are you decommissioning? What's happening there?
Yeah, the superconducting coils are warmed up to room temperature. If any of you have a great idea, let us know, because the ring has made its journey once from Brookhaven to Fermi Lab. So we are open for a G-3 experiment, if you have an idea. But no, in the immediate future, there's no use case for it. Should there be an opportunity, maybe we could revive it, but I think at this moment I would not really say that there's any direct plans for this beautiful magnet. So come grab it if you want it. We can arrange it, hopefully.
So that's maybe also a good finishing word. I don't see any more questions. Thank you again, and congratulations.
Thank you very much. And if you have never gotten any, I hope I have enough. We have these little fridge magnets. That's not the latest iteration, but if you want to have a little memory, we put a magnet on a magnet. So. And I don't know if European magnets are actually good for fridge magnets, so maybe it doesn't work here, but in the US they are pretty common. So come and grab one if you want.
Great. So the next seminar is at the usual time next week. Have a good afternoon.